All right, Adam, you were holding the kendama that was given to me by a fan who came to Brain Candy Live.
Right, and I watched you slowly practice this and get better and better at it during the tour.
Yeah, there was a lot of downtime. There was a lot of time where I was, done with looking at my phone, and I was like, I'm gonna get better and better at this. And I got that much better. But I learned a physics trick that makes it easier.
Okay.
So the point, of course, of a kendama is, well, just to have fun. But one thing you can do is lift the dama, the ball, which has a hole opposite the string, straight up in the air, and then catch it on the spike on the kendama. Pretty clever, right?
Got it.
And it'll fall straight on. Now, it's notoriously hard to do because our hands move in circles.
Right.
And so to go straight up, you really need to just get your legs involved so that you move straight up and you don't lose that hand. Okay? Now, it's not easy, right?
No, clearly. I've tried it. I didn't make any success.
Part of the problem is that any little tilt you give the dama is going to be it's just going to keep rotating while it's in motion, and it'll get worse and worse.
Your lift has to be perfectly linear.
Exactly.
Right.
Or you could just spin the dama.
And have a gyroscope.
Then it's a gyroscope, and it's stable. So if I give it a nice spin and then lift it up, that hole will stay at the bottom, and I can do it just like that, one take. Thank you, physics. The question is, can I design a kendama that is more stable without me having to do this spin? Like, can lifting make it, can lifting make it spin? Can it spin longer? Because what's one of the other problems? This is, only so good at spinning. There's always a bit of wobble, and it'll process just like any gyroscope, but it's already done spinning, and now it's going the other way. Part of it is how the string connects to the dama. Yeah, like that's not a great thing to pivot around.
I'm finding myself wondering if I have. Okay, we're going to do this, and we're going to build you a kendama today.
Go on.
So that's just to make it clear what's about to happen. We're going to build you a kendama, but you want to have as little bias between the string and the ball so that its spinning could be, because one of the things that's causing that precession is the string has friction against the ball.
This actually can come apart, and you can see how it comes together. And I kind of love that flexibility. You can actually adjust just how the cups fit on the spike.
You want to keep that?
I would like to keep that.
So I'm thinking of this material for making your kendama. This is Delrin, otherwise known as acetal. It is a machining plastic. It's one of my favorites because it machines nice and smooth. It's very durable. It is actually a bit of a bearing surface. My question for you is, do you want this handle to be any of a different shape? Would you like it to be longer? I'm assuming that these are all three places to catch the ball, and I noticed that they're different sizes.
Yep, they're different sizes.
These two look the same size, but that one's bigger.
And your hand has to be in different orientations to get the ball on each. There are different ways to hold the kendama. They actually have names, like this is one way, this way would make it easier to catch the ball on the bottom. And I love the physics also of catching the ball in a cup. The best way to do it is to get the cup right underneath the ball just as it has zero velocity. And then you just place it right there. Otherwise, it's going to bounce because these cups aren't that deep. So normally when people first get one, they try to do this. And it hits it, but it falls out. But if you can pull the ball up and then just place it right underneath,
that's awesome.
It's nice, right? And it feels very delicate.
Totally.
So, I don't know. Would I want a longer handle? I mean, since we're making our own custom one, I kind of feel like why not change it all up? But a longer handle might make it more likely to turn, to pivot.
It's hard to say.
It's really hard to say.
I am going to turn the ball first because that's the most complicated part of this arrangement.
Yeah, how do you make a sphere?
This is really cool. I have an attachment for the lathe specifically for making a sphere. I'm going to bring it here and show it to you before I attach it to
Yeah,
the
I'd love to see this.
This is so cool. I only pull this out a couple times a year, but it is a lathe tool specifically for cutting spheres. So
I would not have guessed that.
It clamps into the cross feed of your lathe, and you have to mount it perfectly centered. But when you put a piece of material here,
right,
you can then carve a perfect
and the radius
sphere.
is always the same.
The radius is whatever you want it to be. So you can increase or decrease the radius depending upon, this is for internal radiuses. These two are for external radiuses. So you can carve the bowls with these guys.
And you carve, so you carve a concave with one tool and a convex with another.
Exactly. And the radius is dictated by how far out you mount these little cutting tools.
Right, right.
Jamie Heineman had one for years, and I used it a couple of times in special effects. And when I set myself up with my own lathe, I went looking for this. And they still make them. These are incredibly useful devices.
How long does it take to make a sphere out of Delrin using a lathe and this radii cutter?
It should take me about an hour, give or take.
An hour?
Yeah.
Okay. That's longer than I had expected. Because now that I'm looking at our ability to make spheres of any radius, I'm thinking of the napkin ring paradox.
What's the napkin? Right. Okay. Walk me through the napkin ring paradox. Because if we don't have time to do it today, it's definitely, I remember vaguely.
We might not have time to do it today, but no matter what size a sphere is, when you cut a hole through it like this, but that goes all the way through, you're left with a napkin ring shape.
Right.
You've basically cored the sphere.
Yeah.
And after you core it, it's a little shorter on the top and bottom.
Yeah.
And if you take spheres of very different sizes, but core them so that their height, the height of that napkin ring afterwards is all the same. So imagine like a huge sphere that was cored with a much wider hole. We could make its ring just as tall as this one. Let's say this is like 2 inches. We could core the Earth and be left with a 2-inch tall ring. It would have the circumference of the Earth.
Okay, so let's say we have two balls, one a meter in diameter and one 10 centimeters in diameter. And
we want to make napkin rings out of them that are just 1 inch high.
1 inch high. So we have a 1 inch high napkin ring that's a meter in diameter and a 1 inch high napkin ring that's 10 centimeters in diameter. And what is their relationship?
They have the exact same volume.
Ah, that is so messed up.
Yeah. If we were able to cut the Earth so that it was a ring this tall, it would have the same volume as this with a hole through it. So
it hurts my brain.
Isn't that crazy? I mean,
let's set this up.
Let's set it up.
I have some materials that may even be more ideal than this for trying the napkin ring paradox. But the biggest ring I can cut with this is, I think, a 4-inch diameter.
And what's the smallest?
The smallest is actually however small we want. I could make beads out of this if we really wanted to.
Let's get to the kendama.
Okay, so I'm going to cut the sphere, and we're going to go with this size sphere.
That size.
Okay. Up 2 1/4. Actually, yeah, 2 1/4 inches.
2 1/4.
Actually, it's 2.3. It's a little more than a quarter. I picked up a dial caliper that I think you'll like here. This does metric and English.
Oh.
So metric is on the inside in red, and imperial is on the outside. And when you move this,
it has 2 needles
that move simultaneously.
Wow, so I figured you would just have 1 needle, right? And because the circle would just have been equal, but you're going to go around the circle multiple times.
Yes.
So you need 2 needles.
Isn't that awesome? I didn't even know that I was buying this when I bought it.
You could just sit around and play around and find out when the needles get really close or when they meet each other.
Right, exactly.
And that would be some interesting... Oh, there. What is that?
That is, let's see here. That is 1 centimeter equaling exactly 3.7 0.372 inches. All right, I'm going to set up the radius cutter, and we're going to make a 2.3 inch.
How does the density of Delrin compare to the wood that was used to make this Dama?
It's, I don't think it's very far off. I think it's going to be slightly denser. It's going to be slightly heavier.
That's good, yeah, because the denser the thing, I think the longer we'll be able to get it to keep spinning.
Absolutely. Here we go. Sphere cutting.
All right, so that's just like a huge drill bit holder.
Yes.
What do they call the thing that holds a drill bit?
A chuck.
A chuck.
Yep. So we're going to chuck in and mount securely the Delrin. Because this spins unevenly like that,
yeah.
When I start to lathe it, it puts undue stress on the tool.
Yeah.
And you want to even the stress, because one of the things about Delrin is it can be what you call grippy.
Yeah, so that's like a shock each
You don't
time
want it to grab, and especially
yeah.
if you're working with something like brass, which is super grippy, brass will just completely break in front of you.
Grippy. I totally know what that means, but I'm wondering what the physics are behind why would brass be grippy? What's a really non-grippy material?
Well, steel isn't nearly as grippy. It's not as soft. I'm hazarding a guess here because I haven't looked into the metallurgy, but brass is very soft.
Yeah.
It's very ductile, so it moves.
Right. Like I would imagine a pillow would be really grippy.
Yeah.
Because it would just form around the tool, and then now it's holding on to it.
And there are ways in which different metals do what's called work hardening at different rates. So, like for instance, if you get titanium hot, it becomes much harder. And that's called work hardening. The same thing happens with steel. When you bend a paperclip until it breaks, you're sliding the atoms around each other.
They get hot.
Friction of that heats up and changes the crystalline structure of the steel of the paperclip and causes it to become brittle. And that's why it breaks.
Wow, yeah, I never really questioned why it broke. I just figured it got tired and worn out and gave up.
It gets fatigued.
But it changes its crystalline structure.
Yeah, you're actually tempering it. It's the same way that a blade edge is made hard by heating it at a different rate than the rest of the blade in a Japanese sword or a fine kitchen knife. You're changing the internal crystalline structure to achieve a more brittle knife, which also holds an edge better. So knife making is all about balancing that brittleness with the ductility. You want a flexible back so that it can spring, because if you made an entire Japanese sword as hard as the edge, the moment you hit something with it, it would shatter.
Oh, wow.
Yeah.
Why does a brittle edge hold the blade longer, better?
It's harder. So the harder it is, the more brittle it is. That's the basic gist of it.
And the softer it is,
yeah, so you can take a piece of mild steel and sharpen it really sharp, and it'll cut a couple of tomatoes, and then it'll just lose its edge. Like as it hits the wooden chopping block, it'll start to lose its edge.
So you always want to balance the two.
Yeah. And over time that you lathe, you get the feel for different materials and how fast they want to move. And that's not quite a finished edge because I'm still. You see that unevenness that's still happening there?
Yeah.
That little flash? That's good enough.
All right, so you're going to make a hemisphere at a time. Or
I'm actually going to be able to cut a goodly portion of the sphere off of this.
So it'll go all the way around, and all that'll be left is whatever's connected to
I think so. It's actually, now that you bring this up, it may make sense for me to machine a horn on this, a post. Yeah, actually, I think that makes sense. To machine a post off of this, that I then machine as much of the sphere as I can, cut it off, remount it the other way, and finish off the sphere. This is the order of operations of machining is always a little bit complicated. So with Delrin also, you can remove a fair bit of material at once.
Oh, that's fun.
Isn't that lovely? And you can set things up like this on an auto feed. like this.
Oh. Why would you do that?
If you're making threads, you want to feed it at a constant. There's all these formulas for cutting different types of metric and imperial
so
threading.
What's coming off has the same thickness all the time.
Yes, but also you get a finer quality edge if the feed is super consistent. But it's also more dangerous because you're allowing the machine to automate a process, and that means.
And as we know, the machine has no brain.
Yeah.
Use your own.
And this motor is powerful enough to hurl large chunks of stuff across the shop and through your head. So, like whenever you're auto feeding, you never take your hands off or like take your attention off. Some material removal here. Should give us enough room to work with. Okay.
What other kinds of things do people use a radii cutter for on a lathe?
Actually, the reason we had a radii cutter in Jamie's shop was to make animation armatures. So inside an animated puppet that you move stop motion bit by bit are ball and socket joints, and they're precisely made so that you have balls that you've machined that sit inside of radii that you've machined, and you tighten them to precise tensions for the animator so that the rubber puppet can be moved by its internal
stay
armature.
where it's put.
Yes. Fascinatingly, this was a technology effectively invented by Willis O'Brien to make King Kong, and we're still using almost precise. Like I was at Aardman Animation recently. They're still building the armatures in exactly the same way. Oh, all right. There we go. I can chuck this in, and when I get this to line up, right?
You'll know that it's centered.
Exactly. So now I know that when this sticks out, it is exactly centered on the spindle of the lathe. Okay. Machining work is always all about the order of operations.
Yeah.
And it's whenever I haven't machined in a while, it's the part that I'm the stickiest about. Okay. So we should be all good. Yeah. All right. Let's give it a shot. Here we go. All right. So we're going to unmount this and remount this from the other side. But first I'm going to slice it on the bandsaw. Isn't that lovely?
That is so cool. It's so fun to see it come together a little bit at a time. Much more has to come from here. How are you going to do the poles?
Yeah, that is a good question.
Just make them as thin as possible and then
I think
hand?
so. I'm not exactly sure.
Yeah.
I'm gonna kind of make that up as I go. All right. I'm gonna come in and machine this stuff off. All right. I want to finish this with a bit of a sand because it's going to bring it all into its proper orientation. Give me just a second. Okay, we're almost done. Go ahead and...
Yeah. That is so nice.
Isn't that lovely?
Yeah.
So a little bit of Scotch-Brite. And then
oh, yeah.
This is where you actually machine parts in order to be able to machine parts.
Right, so you're machining a part to hold the ball.
Yes.
So that that part and the ball can go in the chuck.
Exactly.
How do you make it hold the ball firmly enough?
I will show you. It's actually, it's not that complicated. It's pretty straightforward.
Is it just a tight fit?
Well,
it wouldn't seem safe enough.
No, it's, I'll show you. First I'm going to machine a hole, and then I'm going to use a bandsaw to make a slice in that so that it can close around when I chuck it in.
Oh, so okay, that's how you'll
right. So if you'll hold that
and
enjoy that lovely piece.
It's like a doorknob.
Brian May's hair. So I have sliced out on 120-degree increments 3 slots so that when I chuck this into my lathe, it should be able to squeeze in and hold this in a nice orientation. So that should spin. Look at that. No wobble.
Very nice.
I'm very pleased with that. So then I use a cutoff bit to get off. This guy. You've just got to feel out the material.
Go all the way through, or do you make it thin and then you knock it off?
No, I go all the way through.
And then you just fall off.
Yeah.
Yeah, there it is.
So now I want to make my guide for that hole, which I'm going to do with this guy. The reason this bit is used to make centers is it's so highly supported it won't wobble at all when you bring it into a hole.
Ah.
Normal drill bits actually have quite a bit of flexibility to them. Okay. So, now the question is, what is the hole in your Dama?
So, it is actually built in this interesting way where
Yes,
it's got
it's,
a bevel or
chamfered,
whatever,
yeah.
chamfered.
Mm-hmm. So we can, no, it's bigger than that. So it's some weird random.
You know what I'd like to do is, what do you call that funnel shape?
It's a bevel or a chamfer, I think. Yes.
I'd like to not have one because I'm using gyroscopic stability. I don't need that little lip to help me.
You don't want that lip? We can take out the lip. This bit is
just a hole straight through,
15,
not straight
30
through.
seconds. Yeah, almost all the way through.
How deep does it go? Is that important to know?
I don't know if it's it goes that far through.
Because, okay, Adam.
Yes, sir.
Where the string's knot is inside the sphere will affect how much it tilts.
Would you like, but yes.
If the string's knot is right in the middle, there'd be a lot less tilt, wouldn't there? Or less torque would be applied to the sphere when lifted, because you're lifting from the middle of the sphere rather than the edge.
You are potentially right. The question is the
spike. It's right there.
Yeah, the Ken. So right now the spike, it goes directly to center. So we can do the same thing. We can drill this so that this bit goes exactly to the center point.
Right? Yeah.
And then the spike is...
the spike will still catch the ball even if the spike is smaller. And basically it looks like all my instincts are pointing me to making a kendama that makes me look like I'm better than I really am. Let's see, can I... all right, well I can't catch it normally, but I think that's the way to do it.
Okay.
Take advantage of the physics.
Cool. Let me get a shaft collar. I'm just going to put a stop on the drill bit so I can't even go further than that.
I've never seen a drill bit stop.
Oh, yeah. This is a standard thing we do. But you're going to have your knot basically sitting dead center.
Yeah.
Okay.
Ideally, as center as possible.
Yeah. It's totally sound. Oh, and we also need to drill a little tiny hole all the way through.
For the string, right.
I forgot about that.
And what string are we using?
Well, that's a great question. See those two clear drawers over there? The bottom one is string.
Yeah.
Go ahead and open that and we can choose one. I'm happy with this. All right, so I want to, that goes out, this comes out. And that goes there, this goes here. And I want a little tiny hole that goes all the way through that.
Okay, Adam, I've got some string lined up here.
Okay.
Now, I don't know the terminology for describing types of string because I didn't realize how many types of string there are. All right, so here's a kendama.
Yeah.
And then these strings have various, I don't know what you call it, like rigidity.
Yep.
I even put some of this.
It's a monofilament.
Yeah.
Now, I think that the more rigidity you have, so I think we want to look for uniformity and also the lowest profile. So this is probably one of the most uniform, way more uniform than this, which is soft and can change its properties. However, this stuff is the stuff I like the most. This is a high-strength fishing line, 80-pound test, but you feel how thin it is?
Yeah. I feel like this is much better than this. The stiffness is going to impart a lot more torque. It won't.
Yeah. And you want as little bias as possible in the lifting. So both the lightness and the thin profile of this, I think, make it the most ideal. I'm going to get to drilling the hole.
Okay.
Oh, right. Yeah. A pin vise. Where's my pin vise? This will do. There we go. Mm-hmm. I like it. Okay, got to make that hole go all the way through.
Is that a tiny drill?
Uh-huh.
That is cool.
It's called a pin vise, and it's for holding very thin drill bits in a precise orientation. Okay, I'm going to try a different tack on this guy. There it is.
You got it through?
I got a tiny little hole through. We can embiggen it if we need to.
Okay.
But there is your
That
Delrin
looks great. So this larger hole goes to the middle.
Uh-huh.
And then the small one continues.
Precisely.
Okay, so what we really want is I love this density.
Good.
It's gonna spin a lot longer.
Yeah, yeah.
All right, so the string, we don't want the string to twist much. We want it to just kind of be there so that this can spin around.
Oh, I see.
What happened?
What happened was I need to widen the hole out to this because the string can't. Most of the hole is that, and that's too thin for the string. I'm going to go with that, which is a 16th. In order for precision, I'm going to do it like this. This is a lovely little vise for super fine drill bits. Watch this. Yeah, here we go. Oh. This allows me to really feel and make sure I'm not getting too
Yeah,
grippy.
you just push it right with your hand. You feel the resistance.
Yeah, these drill bits can actually shatter, as you can imagine, in a very short order. Okay, and there it's it. Got it through. So, now we'll make a little bit of a knot.
What kind of knot are you doing here?
I'm going to do...
'Cause I only know how to make one knot.
an overhand?
Yeah.
So I have a book on knots that the opening sentence is, the overhand knot is responsible for more lost equipment and lives than any other knot.
So we're not going to use an overhand knot?
No. So a standard overhand is that,
Yep.
right? I go through there. But I get a nice little stacking of rings if I turn this a couple of times and then go through it.
Oh.
It's a modified fishing knot. Oh, I actually turned it the wrong direction. There we go. I end up with this nice little heavy-duty knot.
Yeah.
And then, we could throw a bead on there if you'd like. We can play around with
Like
what
a
that
nice
ends up being.
oily bead.
Yes. Here, go ahead and...
All right, see how this feels. Yeah, that's good. Man, this thing, it's going to spin for a while.
Oh, look at that.
Yeah,
Oh, that's really nice.
that's really nice. Now, when I first spin it, I can't help but give it a little bit of a,
Yeah.
but it evens
Oh, it evens
itself
itself
out.
out. Its own
because
mass.
it's being pulled up as well.
It also seems to be slipping on the string. See that? The string isn't twisting.
The string isn't twisting. That's really important. 'cause
absolutely freaking ideal.
It's so annoying to wait for that.
Go ahead and do it. Yeah, the string is not twisting at all.
So we've got just the
We
right
got exactly
hole
the
for
right
the string to go through.
orientation.
Yeah. I mean,
That's fabulous. Okay, time to make the Ken. All right, we got the Dama. Now it's time for the Ken, the handle, right?
so the Ken, I'm not sure if there's really modifications I want to make. It comes nice as is.
Yeah.
Like it's thinner here, so you've got nice, precise control with your fingertips, and then it's thicker there to rest against your hand.
So you like
So you
that.
get a nice, level, sort of pulled by the ball. I don't know if making the handle longer would affect how I used it.
Okay.
I think it would only cause me to put more torque into the turn.
So you'd rather I leave the handle about the same,
I think
pretty much
so.
the same size?
Yeah. Now, when it comes to the cups.
Yeah, so the cups, I could chuck my sphere cutter in and make these cups exactly spherical, but that's actually not as important. As long as this rim is circular, it sits in the same orientation. So you've got one that's 1 point, give or take 1.35, and then you've got one that's 1.6, and this one is 1.35. Okay, so this and this are identical, and this is 300 thou above.
So how have they built it here? It widens, but it's the spike is pretty much the same width up until like there.
Yeah,
and then it actually
Yes, it has a
Like
it's
a
long
horn
and
shape.
straight before it starts to do a taper. It's a really nifty little bit of construction, how much freedom they give you.
Yeah.
All right, cool. I'm going to use black Delrin. And in fact, I'm also thinking of, for the cups themselves,
Yeah.
white Delrin.
Ah, that would be cool.
Yeah, so we do a little white Delrin for the cup, a little ebony and ivory.
Yeah.
So I'm going to chuck this in and start to work on this before I do the handle. I got to think about the order of operations for the handle first.
Oh, look at it shine.
Yep. Oh, yeah. Just a lovely beast.
Isn't it?
Yeah, I mean, it just... Yeah,
Yeah.
it's really nice. Okay, so now I can retire this guy.
So what are you doing next? The
So now I'm
hole?
going to shape the handle,
Uh-huh.
and the shaping of the handle dictates the hole I drill in the crossbar.
That's correct. Right.
The hole I drill in the crossbar ends up being done on the mill,
Okay.
on the milling machine.
But the handle part that actually goes usually in your palm, that is kind of ornamental, really.
Yes.
Kins can have all kinds of shapes here. Now, you mentioned that this lathe can do threading.
No, not on a taper.
Not on a taper. Because
yeah.
this doesn't have to taper, though. It could just become thicker after it's no longer part of the...
Yeah.
I'm not trying to make this more complicated.
It
I mean, I am.
It definitely complicates it significantly.
It's just that it wouldn't be symmetrical anymore. It would be a chiral helix. That's a very cool thing. And look.
All right, let's see here. Let me...
I get that the taper
I
is an
feel
issue.
you. I feel you. Let's see what I can... I can actually try a sample, and if it works, it could work, and if it doesn't, we don't have to do it. I'm going to start with 8 threads per inch. Let's see.
I so love that you're doing this. I was thinking of it for a long time because as I've been saying, I'm really into asymmetry right now.
Yes. 8 threads is, let's see, LB7Q. All right, we're already on 7. That's Q, B.
And is L low?
And this is X.
L is that one,
L
right?
is, yeah, low. And I probably want to do it on the slow. And I'm going to start, I'm going to start there just as a test. You ready?
Yeah.
Here we go.
Oh, cool. Do you hear that sound? That was the cool police coming to tell us we're doing a good job. It's like a lightsaber.
Wrap your hand and tell me how you like that.
Yeah, that is a professional grade performance kin handle. The tapered part doesn't need threading. We don't have to make it that complicated to do.
No, but I am going to redo that in just a second. I'm going
Why?
to, well, I'll show you because I want this to taper in just a little bit and then I'll recut the threads. Right. Oh, and so now it's also time for us to determine exactly how long you want this threading to last. So the question is, do you want it to go to about like there before it tapers in?
Yeah.
Okay, cool. So I'll do that. And
I see now what you were doing. The cup at the bottom of the handle
yes,
has a bit of a bell shape.
yeah, and I like that it makes it, it'll look a lot more finished.
And it'll stand up on its own.
Yes.
Much better.
So I'm also gonna go a little deeper.
Cool.
And here we go, you ready?
Yeah.
Here we go. Now it's finished top and bottom. So it's got a ring plus a helix.
Oh, so you stopped it from moving forward so it ends on a ring.
Yeah. Look at that. It automatically moves my...
It's moving you forward.
Yeah.
How cool.
So I think what we're looking for is precisely 0.4 inches for that spike.
Nice.
Yeah, all right. Hold this, and we're about to cut this piece off.
Okay. Do you need a different blade?
Nope, I don't.
Oh, there it goes.
There we go.
Wow.
We're getting there, and now it's time to put this bad boy in there.
It's
Something
really
more like
nice
that?
and gentle.
Yeah. Okay, now to drill a hole in the middle of this puppy. And is this drilled in the same spot on both sides?
I was guessing
it is.
Is it? Yeah.
Yeah. Okay, so if this is 2.54, half of 54 is 27. That's 1.27. Now, that is going to go in that.
All right, so a mill is a lathe that's vertical.
Yeah, I guess you could think of that because you could chuck work into the spindle of the mill and work on it with a milling bit you chucked into the vise.
It's interesting that we lathe horizontally for the most part.
There are vertical lathes.
What would you use a vertical lathe for?
I'm not exactly sure.
Just maybe personal preference in some cases?
Well, sometimes it's all about a machine that's big enough to take off chunks of stuff that is heavily resistant to being removed, like steel or iron, and giving it a structure that it won't move or bounce or move out of its own way.
Yeah.
So there are umpteen different versions. There's vertical mills and horizontal mills. There's mills in which the blade is mounted this way and you go at stuff across feet on the table. This whole head is in fact adjustable both this way and this way.
Oh, wow.
Yeah.
So wow, okay.
Yeah. It's a real... a mill is effectively a giant drill press, but it does something that a drill press does not do. And that is you can chuck a thing like this into it. That's an end mill. And I can mill a channel through something by cross-feeding it past.
Oh, right. A drill press isn't going to move in these directions, just up and down.
And to be clear, when I was like 22, I bought a little XY table for my drill press, and I chucked a milling bit in it, and I tried, and it's just like everything. The drill press isn't made to resist that kind of
this
movement.
is what it's so heavy. First of all,
this weighs 3,000 pounds, and its only goal is to not chatter and move when you chuck stuff into it. That's my why.
So the point of a center finder is that it has a point, but it's not gonna start tearing away material.
It's one of the points, but I'm now about to use it for its other main point, and this is totally different. So what I'm going to do is, now I know that that's my Y point. That's my halfway point between either end of this vise.
Yeah.
So that doesn't move, but now I need to know where my X point is, and I need to make sure it's dead center between these two sides.
Yeah.
And because this is a radius, that's actually a little difficult. So what I do is, I come over here, and I come up with a measurement. So you'll watch, see how that's thrown out?
Yeah.
Okay, see how it's way off?
Yeah.
Right there. Now, that's
so
my 0 point.
It's not jiggling because you put it in wrong, it's jiggling by design.
Like
that gets neat.
And so this is exactly 0.2 inches, which means if I remove 0.1, I get the exact edge. Right? So now that's my 0 point, and the question I do is I bring this across this way, and I do the same operation. I go until it's thrown out.
And you go back, and because it's spinning, it gets recentered.
Exactly.
Because when it's not spinning, I can push it, and it doesn't come back to the middle.
Precisely. So now that's 0.8844, which means if I go to 0.4422, I'm at the exact midpoint.
So from one side to the other, you've just done 2, divide it by 2, and it gives you...
And that gives me my dead center point. Now, I also know that it is not entirely the most accurate way to chuck the center finder into a drill chuck. I'm aware of that, but I'm also lazy.
What's wrong with using a drill chuck?
The drill chuck is just, it's not the most accurate way.
It's not as precise?
It's not as precise. It could be off by 2 or 3 thou, which in precise machining is significant.
And when you're as good at kendama as me, doesn't matter.
Exactly. So now I want to make sure my drill bit doesn't wander. And that's a whole, that's again, I'm going to bring out the center drill. And this makes sure, if you drilled a normal drill bit, even onto this soft material, and you come into it and you hit it, it could move because it's a curved surface that it's facing. This allows me, that allows me to make sure my hole is perfectly centered so that when I bring in the drill bit, that is 0.412, and I think this is 0.4, that's actually going to be quite a pressure fit. I'm going to go a little slower. There.
Nice.
And now I'm assured, because of the measurements I made, that that hole is precisely centered on the X and the Y axis. Okay, I want to remove a little bit of that chamfer. This is cool. This is a deburring tool. It takes a burred edge and just like peels it off.
Peels it right off.
Just makes everything look a little neater. And now the string. How does the string attach? The string attaches.
Well, there's two holes. One thick enough for a knot to fit in, and then one tiny enough for just the string.
That's totally easy for us to do. That's pretty darn good.
That's good. That's good.
Okay, so now we need a heavier drill bit. That's a 16th, so that we can get rid of the knot.
Yeah.
Okay. So, oh right.
Yes, we reach a decision point. How long is the string?
However long you want it to be. I think you should start with that length. I think you should start with exactly this length, and then, if you need it longer, we just give you some more string to take home and you can try it.
I think that, we start with this length. The reason I'm tempted by a longer string is that we've built a Dama that should be able to be stable even for even longer.
This is true.
I'm imagining myself on top of the Empire State Building with the Dama hanging down by the sidewalk, and I'm still able to pull it up and it doesn't tilt, and I'm still able to spear it.
That is a pretty bold statement right there.
The length of the string here is actually exactly 18 inches from where it leaves the kin to when it enters the Dama.
All right, I'm going to mark that, and I'm going to just secure that end. And
not bad.
Not bad. I'm pretty pleased with that. Okay, so when that goes in, yep, look at that.
Nice and tight,
okay, good. Yep. And we are gonna, that was a figure 8 knot I put in there, by the way.
Why'd you choose figure 8 instead of the 3-looped overhand?
It was just, wouldn't have had as much control over the 3 loops.
Nice and flush.
Yeah, nice and flush. So then we bring in this guy. Yep, that's totally working. And this, there you go. Michael, there is your homemade Delrin. Oh, wait, you got a little burr here. There, your homemade Delrin Kendama.
Look how awesome the color scheme is and the threading.
I thought you'd like the black and white.
Adam, I want you to be the first to juggle with it.
All right.
Nice!
Without the spinning!
Without the spinning. Let's compare how the Damas hang, because yours seemed quite short, but
it is
look
a little
at that.
shorter.
And I think that may have made it more difficult for you.
It could have. I'm going to give you, 50 or 60 feet of this string, so you have all that you need to try multiple different kendama lengths.
Wow, the difference in weight is really surprising. It's pretty incredible.
Really?
All right, here, I'm going to try a no spin. I think having this string so much shorter does enhance the difficulty.
And you may end up experimenting with different kinds of knots that give you different beauty.
Yeah. That's going to be extremely easy to catch. There's just the issue of the length of the string to play around with, and then exactly how the string is secured to the dama.
And you may find other strings are even better. You may find, you may add a bead. Yeah, there's all sorts of different ways to play around with this.
What an interesting mechanism, too, for that string to pull through.
Yeah, I know. It's fascinating. And the plastic will move, but it won't wear down as much as the wood will. Hey! Nice. Oh!
And by the way, we're doing this with no beveled edge to help us get that spike in.
Right. You went to an increased level of difficulty.
Yes.
I'm very pleased.
I'm very pleased. Adam, thank you.
So,
we're going to hug it.
We're going to hug it out.
Of course.
That's awesome.
What was I thinking?
That is a lovely one-day build.
It looks scary. This looks like, oh, hey, I'm a free
my
spirit.
European kid's toy that's made of wood and it's natural. And this looks like
looks like airport security's not going to let me through.
Exactly.
And they shouldn't, because that's a lot of momentum.
Right. Yeah.
You could knock someone out with this. And it's dense. It's not going to hit something and get dented. It's going to leave the dent in the thing.
If you bring the both of them, then this one gets the harmlessness by association.
Yeah. See, they're friends.
Yeah, see?
Despite their different philosophies. And you know what? They're mirror images of each other. Because of the way the string comes out. The big cup is on the left and the right.
Look at that. I made them chiral.
I noticed that as soon as I was holding it, because I'm used to catching the ball and the big cup's a turn clockwise.
Certainly.
Now that could be, actually you can't change that because this hole is here.
No, but I mean you could re-drill the hole on the other side. Certainly.
I think it's best to learn both ways.
Like Jimi Hendrix could play left-handed and right-handed.
Everyone's like, oh, Michael Stevens uses a left-handed Kendama. Put that on my IMDb page. Cool. Adam, thank you.
Dude, my absolute pleasure. That was a lot of fun.